Hello, class, and welcome. Today, we are beginning a new and exciting topic in mathematics. We'll be diving into Chapter 9, which is all about differentiation. Before we jump into the details, let's talk about the big picture. What is differentiation all about? At its core, differentiation is the mathematical tool we use to describe the rate of change between two variables. Think about how quickly a car's speed changes, or how a company's profit changes with its advertising budget. These are rates of change. And because rates of change are everywhere, understanding them allows us to model, interpret, and analyze a huge variety of real-world problems and situations. Furthermore, differentiation helps us understand the behavior of functions. It lets us find the peaks and valleys of a graph, determine where a function is increasing or decreasing, and pinpoint its steepest points. In other words, it allows us to interpret the key features of a function's graph. So what will you be able to do by the end of this chapter? Let's look at our learning objectives. You will learn how to estimate limits, understand the gradient of a curve, use different notations for the derivative, find where functions are increasing or decreasing, interpret the meaning of the derivative sign, differentiate certain types of functions, and find the equations of tangent and normal lines. We'll unpack all of these ideas one by one. The central concept that ties all of this together is the derivative. We can think about the derivative in two main ways. Physically, it represents a rate of change. Geometrically, it represents the gradient or the slope of a function's graph at a specific point. This relationship between a function and its gradient, its rate of change, can be expressed both graphically and algebraically, and we'll explore both representations. Think about the images here. For the sprinters, their position changes over time. Their speed is the rate of change of distance with respect to time. At the exact moment they leave the blocks, their speed is changing rapidly. That's a concept we can model with differentiation. For the students, perhaps we could model the rate at which they learn or solve problems. Differentiation gives us the language to talk about these kinds of dynamic changes precisely. Now, let's begin with the foundational concept that makes differentiation possible, the limit. All right, let's start with our first main topic, Section 9a, Limits and Derivatives. We're going to begin with an introduction to the concept of a limit. So what is a limit? Imagine we have a function f of x, and we want to know what value the function gets close to as x gets close to some number. Let's call it a. This idea of getting closer and closer is the essence of a limit. We're interested in the journey, not necessarily the destination. Let's look at a straightforward example. Consider the function f of x equals 2x plus 3. This is a simple linear function. Let's investigate how this function behaves when x is very close to 2. Of course, we can just calculate f of 2 directly. 2 times 2 is 4, plus 3 is 7. So f of 2 equals 7, that's clear. But to understand limits, let's pretend we can't plug in 2. Let's just see what happens as we get infinitely close to 2. First, let's approach 2 from the left side, using values that are slightly less than 2. If x is 1.9, f of x is 6.8. If x is 1.99, f of x is 6.98. If x is 1.999, f of x is 6.998. It seems pretty clear that as x gets closer to 2 from the left, f of x gets closer to 7. Now let's do the same from the right side, using values slightly greater than 2. If x is 2.1, f of x is 7.2. If x is 2.01, f of x is 7.02. If x is 2.01, f of x is 7.002. Again, as x gets closer to 2 from the right, f of x is clearly getting closer to 7. Since the function approaches the same value 7 from both the left and the right, we can state what the limit is. We write this using this special notation. The limit of f of x as x approaches 2 is 7. This statement means that as x gets arbitrarily close to 2, the value of f of x gets arbitrarily close to 7. These approaches from the left and right are called side limits or one-sided limits. The limit from the left is written with a small minus sign, and the limit from the right is written with a small plus sign. For the overall limit to exist, both the left-hand and right-hand limits must exist, and they must be equal. In this case, they are both 7, so the limit is 7. Now you might be thinking, this is silly, I could have just plugged in 2 to get 7. And in this case, you'd be right. But what happens when we can't just plug in the number? Let's explore a case where the limit is not so simple, a situation where we cannot just calculate f of a directly. The main reason we can't do this is when we encounter division by zero. If the denominator of a fraction is zero, the expression is undefined. However, if both the numerator and the denominator are zero, we have what's called an indeterminate form, and it's possible that a limit still exists. Let's see an example. Consider the function f of x equals sine of x divided by x. What is the limit of this function as x approaches 0? Let's try to calculate f of 0. We get sine of 0, which is 0 divided by 0. This is undefined. We cannot calculate the value directly, so we must use limits to investigate. Let's first look at the graph of the function. It's an interesting wave-like shape that dampens as x moves away from 0. Notice that at x equals 0, I've drawn an open circle. This indicates that the function is not defined at that exact point. But from the graph, it certainly looks like the function is heading towards a specific value as x gets close to 0. To be more precise, let's use a table of values, just like we did before. Let's take values of x very close to 0 from both the negative and positive sides. At negative 0.1, the function value is about 0.998. At negative 0.01, it's 0.9998, and at negative 0.001, it's extremely close to 1. The same thing happens from the positive side. As x gets closer and closer to 0, the function value gets closer and closer to 1. So even though f of 0 is undefined, the function approaches a clear value. Therefore, we can conclude that the limit of sine of x over x as x approaches 0 is equal to 1. This is a very famous and important limit in calculus. It shows that the concept of a limit is more powerful than simple substitution, as it allows us to analyze a function's behavior at points where it isn't even defined. Now, what happens if a function doesn't approach a nice finite number? What if it blows up and goes to infinity? This is also possible. A limit can be positive infinity or negative infinity. Let's look at a classic example. Consider the function f of x equals 1 over x. Here's the graph of the function. We can see something dramatic happens near x equals 0. The function is not defined at x equals 0 because that would mean dividing by 0. Let's investigate the one-sided limits as x approaches 0. First, let's approach 0 from the right side through small positive numbers. Think about 1 divided by 0.1, which is 10, then 1 divided by 0.01, which is 100, then 1 divided by 0.001, which is 1,000. As the denominator gets smaller and smaller, the value of the fraction gets larger and larger without bound. So the limit as x approaches 0 from the right is positive infinity. Now let's approach 0 from the left side through small negative numbers. 1 divided by negative 0.1 is negative 10. 1 divided by negative 0.01 is negative 100. As x approaches 0 from the left, the value of the function becomes a larger and larger negative number. So the limit as x approaches 0 from the left is negative infinity. Since the one-sided limits go to positive and negative infinity, the overall limit at x equals 0 does not exist. But these infinite limits tell us something very important about the graph. In general, if the limit of a function as x approaches a number a from the left or the right is positive or negative infinity, we say that the vertical line x equals a is a vertical asymptote of the graph. It's a vertical line that the graph gets infinitely close to but never touches. So for our function f of x equals 1 over x, the line x equals 0, which is the y-axis, is a vertical asymptote. This is the formal justification for the asymptote we see on the graph. We've talked about what happens when x approaches a finite number, but what about the end behavior of a function? What happens when x gets incredibly large, either in the positive or negative direction? For this, we use limits at infinity. We look at the limit of f of x as x approaches positive infinity or as x approaches negative infinity. Let's return to our example, f of x equals 1 over x, to see what this means. Look at the graph again. What happens as x gets very large and positive, moving far to the right? Think about it. 1 divided by 1,000, 1 divided by 1 million, 1 divided by 1 billion. As the denominator gets infinitely large, the value of the fraction gets infinitely small, approaching 0. So the limit of 1 over x as x approaches positive infinity is 0. The same thing happens as x approaches negative infinity. 1 divided by negative 1 million is a very small negative number, very close to 0. So the limit as x approaches negative infinity is also 0. This behavior, where the function approaches a specific finite value as x goes to infinity, defines another key feature of a graph. In general, if the limit of f of x as x approaches positive or negative infinity is a finite number L, then we say the horizontal line y equals L is a horizontal asymptote. It's a line that the graph approaches as x goes to infinity. So for f of x equals 1 over x, the line y equals 0, which is the x-axis, is a horizontal asymptote. Let's look at another quick example. Consider f of x equals the quantity x minus 3 divided by the quantity x minus 2. The graph shows a vertical asymptote at x equals 2 because the denominator is 0 there. It also shows a horizontal asymptote at y equals 1. This is because as x gets very large, the minus 3 and minus 2 become insignificant, and the function behaves like x divided by x, which is 1. So the limit as x approaches infinity is 1. Let's solidify our understanding of asymptotes with two more examples involving different types of functions. First, consider the function f of x equals 20 times e to the power of negative x plus 10. Here's the graph. This is an exponential decay function that has been shifted up by 10 units. Let's think about the horizontal asymptote. We need to find the limit as x approaches infinity. We need to evaluate the limit of 20 e to the negative x plus 10 as x approaches positive infinity. As x becomes a very large positive number, negative x becomes a very large negative number, and e raised to a large negative power is very, very close to 0. So the e to the negative x term goes to 0, 20 times 0 is 0, and 0 plus 10 is 10. Therefore, the limit is 10. This confirms our formal justification. The line y equals 10 is a horizontal asymptote for this function, which is exactly what we see on the graph. Now for a second example, this time with a logarithm, consider g of x equals the natural logarithm of x minus 4. The natural logarithm function is only defined for positive inputs. Therefore, x minus 4 must be greater than 0, which means x must be greater than 4. This tells us something important happens at x equals 4. Let's find the limit as x approaches 4 from the right side, which is the edge of its domain. We need to evaluate the limit of the natural log of x minus 4 as x approaches 4 from the right. As x gets very close to 4 from the right, the term x minus 4 becomes a very small positive number. The natural logarithm of a number that is approaching 0 is negative infinity. So the limit is negative infinity. This is our formal justification. Therefore, the line x equals 4 is a vertical asymptote for the function g of x, which again is exactly what the graph shows. Now let's look at one of the most important and interesting limits in all of mathematics. This limit provides the definition for a very special irrational number. I'm talking about the number e, which you've seen in the context of exponential and logarithmic functions. It's approximately 2.71828. But where does this number actually come from? It comes from a limit. Let's investigate informally the limit of the quantity 1 plus 1 over x, all raised to the power of x as x approaches positive infinity. This is a strange one. As x goes to infinity, 1 over x goes to 0, so the part in the parentheses goes to 1, but the exponent is going to infinity. So is the answer 1? Is it infinity? It's not obvious. This is another indeterminate form. Let's see what happens when we plug in some very large values for x. If we let x be 1,000, the expression evaluates to about 2.7169. If we let x be 1,000,000, it evaluates to 2.7182804. If we use an even larger number, like 10 to the power of 10, we get 2.71822818. Notice a pattern? The value seems to be settling down or converging to a specific number. In fact, the resulting limit is precisely the number e. This is the formal definition of the number e. It's the value that this specific expression approaches as x becomes infinitely large. This limit is fundamental in many areas of science, finance, and mathematics, particularly in problems involving continuous growth. Now that we have a solid understanding of limits, we can finally connect them to our main topic, the derivative. We're going to interpret the derivative as a gradient function and as a rate of change. One of the most important uses of limits in calculus is finding the gradient or slope of a curve. For a straight line, the gradient is constant. But what about a curve? The steepness of a curve is constantly changing. So how can we talk about the gradient at a single point on a curve like this point P? The answer is to use a tangent line. This is a crucial idea. The gradient of a curve at a specific point is defined as the gradient of the straight line that is tangent to the curve at that exact point. A tangent line just touches the curve at one point without crossing through it. So the problem of finding the slope of a curve has been transformed into a new problem, finding the slope of a tangent line. But how do we do that? If you try to just draw a tangent line by hand and measure its slope, you'll find it's very difficult to be accurate. We need a more precise analytical method, and this is where limits come in. So how do we use limits to find the exact gradient of the tangent line? The idea is to start with something we can calculate, the gradient of a line that passes through 2 points on the curve. This is called a secant line. Let's say we want the gradient at point P. We can pick another point on the curve, let's call it Q1, and draw a straight line through P and Q1. This is a secant line. We can easily calculate its gradient using rise over run. Now, this secant line's gradient is an approximation of the tangent line's gradient at P, but it's not a very good one. How can we improve it? The key insight is to move the second point Q closer and closer to our target point P. Look what happens to the secant line as I move Q2 closer to P and then Q3 even closer. The secant line pivots and gets closer and closer to looking like the actual tangible tangent line at P. The gradient of the secant line is approaching the gradient of the tangent line. This sounds like a limit, doesn't it? And that's exactly what it is. The gradient of the tangent at a point is the limit of the gradients of these secant lines as the second point gets infinitely close to the first. This is the fundamental link between limits and derivatives. The gradient of a chord or secant line is written as delta y over delta x, which just means change in y divided by change in x. The great mathematician Gottfried Leibniz adapted this notation. He reasoned that for an infinitesimally small change, a delta becomes a d. So the gradient of the tangent, the derivative, is written as dy over dx. This represents the limit of delta y over delta x as the change tends towards 0. Let's make this concrete with a worked example. We're going to find the gradient of a curve at a specific point using this limit process. Let's take the function y equals x squared. We want to find the gradient of the curve exactly at the point P, which has coordinates 4, 16. To do this, we'll pick a second point Q with coordinates x, y, and we'll look at the gradient of the secant line PQ. We will then see what happens to this gradient as we let Q slide along the curve towards P. We'll organize our calculations in a table. Our table will have columns for the x-coordinate of Q, the corresponding y-coordinate, the change in x, which is delta x, the change in y, delta y, and finally the gradient of the chord PQ, which is delta y divided by delta x. Let's start with a point that's a bit far away. Let's pick Q to be at x equals 5. If x is 5, then y is 5 squared, which is 25. The change in x, delta x, is 5 minus 4, which is 1. The change in y, delta y, is 25 minus 16, which is 9. So the gradient of the chord is y over delta x, or 9 divided by 1, which is 9. Now let's move Q closer. Let's try x equals 4.5. If x is 4.5, y is 4.5 squared, or 0.25. d2x is 4.5 minus 4, which is 0.5. Delta y is 20.25 minus 16, which is 4.25. The gradient is 4.25 divided by 0.5, which is 8.5. Notice the gradient got a bit smaller. Let's get even closer. Let x equal 4.1. If x is 4.1, y is 16.81, delta x is 0.1, delta y is 0.81, the gradient is 0.81 divided by 0.1, which is 8.1. We're getting closer. One more time, let's get extremely close. Let x equal 4.01. If x is 4.01, y is 16.801, delta x is 0.01, delta y is 0.801, the gradient is 0.0801 divided by 0.01, which is 8.01. What value does the gradient appear to be tending towards? The sequence of gradients is 9, 8.5, 8.1, 8.01. It's clearly getting closer and closer to 8. This suggests that the limit of the gradient of the chord is 8. And because the gradient of the tangent is the limit of the gradient of the secant lines, this tells us that the exact gradient of the curve y equals x squared at the point 4, 16 is 8. We've now seen that this process of finding the gradient of a curve is called differentiation. The result of differentiation is called the derivative. The derivative can also be called the slope function or the gradient function, because for any given x value, it gives you the value of the slope or gradient of the original function's graph at that point. It's important to be familiar with the different ways we can write down the derivative. There are several common notations. We've already seen Leibniz's notation, dy over dx. This is very descriptive as it reminds us of change in y over change in x. If we had a graph of a variable g against a variable t, the derivative would be dg over dt. Another very common notation is Lagrange's notation. If the function is f of x, then its derivative is written as f prime of x. This prime symbol indicates that we have taken the derivative. In physics, especially when dealing with derivatives with respect to time, you'll often see Newton's notation. A dot over the variable, like x dot, is used to represent dx over dt, or the rate of change with respect to time. So we have these two interpretations of the derivative. Geometrically, it's the slope of the tangent line, but what about the other interpretation? The derivative also tells you the instantaneous rate of change of y with respect to x. It's not an average rate of change over an interval, but the exact rate of change at a single moment or point. This is an incredibly powerful idea. If you have a function describing a car's position over time, its derivative gives you its instantaneous velocity. If you have a function for a company's profit, its derivative tells you the instantaneous rate at which profit is changing. This idea of the derivative as a rate of change allows us to create powerful mathematical models of the world. In many real-life situations, we might not know the function itself, but we might have an idea about its rate of change. This allows us to set up an equation involving a derivative. These models, which are equations that contain derivatives, are called differential equations. Creating and solving these is one of the most important applications of calculus. Let's look at a simple example of how to translate a real-world statement about a rate of change into a mathematical equation. Here's the scenario. The rate of growth of a bacterial population which has size n over time t is proportional to the current population size. This makes sense. The more bacteria you have, the faster the population grows. How do we write this as an equation? Let's break it down. First, the phrase the rate of growth of n over time t is a perfect description of a derivative. It's the instantaneous rate of change of the population n with respect to time t. So we can write this as dn over dt. Next, the sentence says this rate of change is proportional to the population size, which is n. The symbol for proportionality is this alpha-like symbol. So we can write that dn over dt is proportional to n. This is a good start, but a proportionality is not an equation. To make it an equation, we need to introduce a constant. To turn a direct proportion into an equation, we introduce a constant of proportionality, which we'll call k. So our final differential equation is dn over dt equals k times n. This equation is a mathematical model of the bacterial growth. This is a fundamental model for many types of growth, from populations to radioactive decay to compound interest. It all starts with translating a statement about a rate of change into a derivative. Let's take a moment to recap the main ideas we've covered today. First, we introduced the crucial concept of a limit. The limit tells us what value a function approaches as its input gets closer and closer to a certain point. We saw that this is a more powerful idea than simple substitution, as it allows us to handle undefined points and investigate end behavior. We used limits to formally define asymptotes. Vertical asymptotes occur where a function's limit is infinite, and horizontal asymptotes are determined by the function's limit as x approaches positive or negative infinity. Most importantly, we use the concept of a limit to define the derivative. We saw that the derivative, which gives the slope of a curve at a point, is the limit of the slope of secant lines as they become infinitesimally small. Finally, we established the two fundamental interpretations of the derivative. Geometrically, it is the slope of the tangent line to a function's graph. Physically, it represents the instantaneous rate of change of one variable with respect to another. We have successfully estimated limits from tables and graphs, and we've developed an informal understanding of the gradient of a curve as a limit. In our upcoming lessons, we will build on this foundation to learn the rules for calculating derivatives and applying them to solve a wide range of problems. Thank you.